Друзья, добрый день всем. Мы начинаем наш очередной вебинар. Сегодня у нас, к сожалению, не очень много участников, но тем не менее достаточное все-таки количество, я думаю. Возможно, одна из причин, почему не очень много, потому что сегодня будет такой непростой на английском языке вебинар. Но мы попробуем его провести, тем не менее. Значит, сегодня 6 ноября 2024 года и московское время 16 часов 4 минуты. Сегодня доклад Эдварда Льюиса, Соединенные Штаты, штат Иллинойс, который вот нам, по сути дела, два доклада сделает в одном вебинаре, которому не удалось выступить по техническим причинам на конференции. Ну, зато сегодня, может быть, мы более расширенно это сможем все послушать. Значит, первый доклад, вот, по сути дела, я его называю исторический, что нового может нам в физику может внести, физику нашу, вот Ленар-физику может внести изучение микроплазмоидов. И вторая – это характеристики шаровой молнии, позволяют понять странное излучение. Вот, значит, вот такие из двух частей будет состоять доклад. И, значит, вот Эдвард Льюис, он, кстати, почему-то убежал, сейчас вот я вижу, его нет. Ну, по-русски я говорю, поэтому ему это не интересно. Значит, он очень, скажу так, вот с очень большим вниманием отнесся к этому выступлению, и он специально подготовил презентации на русском языке. Вот у нас будут sorry, I speak in Russian. I wanted to say some words in Russian. Our auditorium better understand Russian. You understand, you know that in English. And after that, I give you floor. But now, 2-3 minutes I will speak in Russian. Значит, вот возвращаюсь. Вот он очень внимательно отнесся к этому вебинару и подготовил специально для нашей аудитории, подготовил специальные виды своей презентации на русском языке. И я вам ее 3 часа назад разослал. Если, может быть, вы ее не смотрели, я вот рекомендую там как-то смотреть. Это первое. Второе, насколько я понимаю, Эдвард Льюис будет именно по русским этим презентациям двигаться, вот этим слайдам, подготовленным для русской аудитории, для русскоговорящей аудитории. Вот. И это тоже огромное ему спасибо за это. Пару слов про Льюиса. Он сравнительно новый у нас человек. Он возник где-то примерно год назад. И возник он с подачи вот Анатолия Ильича Никитина, который с ним знаком уже давно, как я понимаю, поскольку они вот работают в области шаровой молнии. И сегодняшний доклад, вот он очень протягивает мостик дополнительный между шаровой молнией и холодным синтезом, потому что мы все как-то вот интуитивно чувствуем, что это вещи очень близкие, шаровая молния и холодный синтез, но каких-то вот пока прямых доказательств нет. И вот одна из идей о том, что это очень связанные вещи, это то, что шаровые молнии вот являются некоторой формой неизвестного, как я называю, излучения, а его большинство называют по тому термину, который ввел в свое время Рудской, странному излучению. Я напомню, что понятие, ну вот если Леонид Ирбекович Рудской он ввел термин «странное излучение», то сейчас более или менее понятно, что это как бы излучение, конечно, но это частицы в первую очередь. Вот. И все мы знаем, что масса людей, вот, работающих активно в области холодного синтеза, они вводят разного рода частицы для того, чтобы, или группы частиц для того, чтобы объяснять явления, которые мы наблюдаем в наших экспериментах. Вот о некоторых из них сегодня тоже будет рассказывать Эдвард Льюис. Ну, вот идея о том, что шаровые молнии и странные излучения и нашей аудитории, и на наш Никитин Анатолий Ильич. Он, кстати, по-моему, сегодня присутствует. Вот. Но он, возможно, эту идею как бы вот они вот в этом кругу Льюис, Никитин как-то уже обсуждают довольно давно. То есть как-то это вот эти идеи и у Никитина тоже связаны с работой с Льюисом. Но вот сегодня Льюис свой персональный взгляд. Теперь смотрите, выступать Эдвард Льюис будет на английском языке. Вот. Вопросы мы ему задаем на английском языке и получаем ответы на английском языке. Я предупредил Эдварда, что необходимо говорить очень коротко, очень понятными, простыми словами. По-моему, он эту идею понял. В отличие от Боба Гринье, который, вот я ему 100 раз уже говорил, хай, Боб, я ему 100 раз говорил, что Боб, please, пожалуйста, говори медленно, коротко и очень простыми словами. И он никак, вот он не может, он такой активный человек, и вот он сразу начинает очень сложный английский применять в изложении. Попробуем сегодня все-таки проблему языковую каким-то образом преодолеть. А вот выступление, Боб, он смеется, потому что у него там переводчик есть, он с запозданием дает, и поэтому, значит, вот Боб понял, о чем я говорю. Значит, попробуем преодолеть языковую проблему, а вот выступать, и я сейчас это объясню Эдварду Льюису, а выступать уже после докладов я предлагаю, потому что это очень сложно выступать, давайте будем выступать по-русски, а он уже, Эдвард Льюис, потом, просматривая записи, сможет как-то это учесть в своей дальнейшей работе или, может быть, даже ответить авторам выступления. Друзья, я закончил, и я передаю слово Эдварду Льюис. Эд, please switch on your microphone. This is first. Switch on your microphone. You should. Okay. You find this button.
I found it. Yeah.
Sorry for my more or less long introduction in Russian. I explained for our auditorium that you will talk in English, but I asked you to use simple words, short, simple sentences, and pronounce words very clearly. It's for better understanding. This is first. And second, Ed,
Yeah.
questions to you after presentation, and your answers will be also in English. But discussion will be in Russian, and you may understand what we will talk in discussion after presentation, looking on the video record of our webinar tonight or next day.
Right.
This is my proposal, to mainly in English, but discussion finally in Russian, because for us to use English, it's very difficult to explain what we would like to say. It's absolutely impossible for us to use English. Okay, and I see you succeeded in showing us your presentation. Thank you very much. And
Okay.
I give you floor. Please start your presentation.
All right. Okay. So my presentation. Well, first, Добрый вечер. Is that good? Добрый вечер. So it's okay. So my presentation first is going to be about the history of science. Can you see this very clearly on your side?
I see, but we see, but I explained for auditorium that you will use Russian,
Right.
Russian. Oh, okay. This is next slide.
That's
Okay,
right.
we see you. Everything is okay.
Everything is
Continue.
okay, good. All right, so this is my presentation, and this is my website. So if you're interested in my website, it's scientificrevolutions.com, and I have videos I made about 10 years ago with kind of like a interview. You can go there. Okay, so okay, my presentation is about how paradigm shifts in physics causes the contraritive wave. But first of all, that there are paradigm shifts. So every 80 years, since the history here, yeah, every 80 years since Copernicus, approximately every 80 years, as averages to 80 years, there's a paradigm shift in physics. The paradigm shift, um, so you can read this, started in 1506 here, right? And um, And this is when the heliocentric theory started. So here you can see there it started from Copernicus, right? To
It's
was
it's better.
heliocentric
It's better.
theory,
Yeah.
right?
Uh-huh.
And then Gilbert, let me see here. Yeah, Gilbert, um, who lived in England, Galileo, Kepler, and then Newton, right? So everybody's aware of this. Newtonian physics was a paradigm. Most people realize that Galileo, around this time, there was another paradigm. Okay, so then there was a Franklin paradigm. It was a paradigm that had to do with fluids. Huh?
Just a moment. Just a moment. I asked you to pronounce every words very, very clear. Please take into account the ability Russians to understand English words. Very
Okay,
clear
so
every words, please. Every
yeah,
words.
so
Uh-huh.
yeah,
Try to do that. Try to do that. I know that it's not easy, but try to do that.
okay, so Benjamin Franklin lived in North America in 17, I think he was born in 1705, maybe something like this. Anyway, he started fluid theory. He was the first person to talk about there is a fluid or a matter, he called it matter of heat, matter of electricity. Newton didn't talk about energy in this way. To Franklin, these fluids were conserved. And this was the major achievement that Franklin introduced into physics, that energy, electricity and magnetism are conserved entities, which is a new concept in physics. And so this started here with Lavoisier, Coulomb, and then a man named Aepinus, Aepinus, who developed a theory of magnetism. And then there was Lavoisier developed a theory of chemistry, or it was called fluid caloric chemistry. Then there was an industrial revolution here before the time of Faraday. In 1780, an industrial revolution started based on this theory, based on the theory of heat that Franklin introduced. So James Watt developed a steam engine, and then there was a development of chemical industries here in about 1790. And then starting here, there was a big increase in productivity. Okay, so, and then there was also a crisis period here. Not Faraday, actually, Oersted showed that electricity and magnetism are not separate fluids, but they are the same thing. It was called electromagnetism, right? And Faraday showed or tried to introduce the idea that um, there's an electromagnetic line of force. So he introduced this new concept, and that also that atoms are point atoms. They're not, as Newton and Franklin thought atoms were very hard, small objects, right? Very small, but an object. But Faraday taught they're not objects, they're lines, they're points from where lines of force originate. And so then this allowed Maxwell around 1860, he took this this concept and developed a classical field theory. And then there was another crisis period before Einstein where they found many anomalies, right? And so this is my presentation. It's that every 80 years, uh, yeah, every 80 years there's a crisis period that lasts 10 to 20 years. I don't know if anybody in Russia reads The Structure of Scientific Revolutions, but it's a in the West, in the U.S., it's a kind of famous book. If you're interested in science or philosophy of science, we read History of Scientific Revolutions by Thomas Kuhn. So here's that, and you can read that. So okay, so this concept of paradigm shift was originated by him. Wow, what happened here? There it is. Yeah. So wait, let me get up here. I'm having trouble here, so let's see. I want to go to, try to get up here. This is a long slide. I'm going to have to go very fast, actually. Oh, here. Sorry, I don't know how to use my own software here. Okay, so 11, 10, 9, 8, 80 years, there it is. Okay, so there's a crisis period. Okay, there was another crisis period from 1971 to 1992, and you can see that um, among the people who introduced, um, who introduced some new concepts was actually Derryagin, um, who he was very influential in Russia, actually Soviet Union back in the 1990s, and he one of his students was Andrei Lipson, and Lipson was known in the U.S. because he worked here at the University of Illinois, and I met him. They were working on superconductivity. It's trying to find evidence for superconductivity here, but in code fusion reactions. Okay, so here's so yeah, these okay. So first was Derryagin, and then in the 1980s was Ken Shoulders, right? First Derryagin in the 70s talked about polywater. Ken Shoulders did a lot of research independently and somewhat secretly. He was quite secretive. In 1987, Ken Shoulders wrote a book called EV's The Tale of Discovery, but he kept this book secret. He gave it to very few people. So it was a secret book that I never read until about 5 years ago. Now you can read this book online because people are putting it online. But back then it was a secret book, and so it was interesting. You had to pay about $400 to buy his book. So okay, so yeah, so there's Ken Shoulders, and then there is 1986 superconductivity was discovered. 1989, Fleischmann and Pons and told the world about fusion, about finding transmutation happening in their electrodes. But as everybody knows, and as you know, this field died, right? It basically nobody, after a lot of really controversy, a lot of problems, a lot of I don't know what happened. The field was put down by 1997 in the U.S. It was almost dead. But in Japan, Takaaki Matsumoto here discovered the mission of strange objects. But he didn't know what they were. He wrote an article, and I read about it one morning where he was talking about, I have found rings on my detector sheets, nuclear emulsions. But he said he didn't know what they were. So as I was reading it, I realized that ball lightning makes rings. I knew this from studying a lot about ball lightning that sometimes when the ball lightning touches the ground, or if it touches an object, it'll make a ring on the object. You know, a ring trace we call it, or tract. And so, sorry, I can't read my things here. Yeah, there. So here's an example of the rings. Around 1992, 1991, Matsumoto started finding rings like this. So they were published in Fusion Technology, and he So there's 3 rings, and I think many of you, if you've done experiments, may have found rings, but I'm not sure why. One thing I don't understand is Ken Shoulders and Matsumoto usually found rings. They found something like a ring. They didn't find. Russians are usually finding another kind of trace, and I don't know why. So here, um, so um, so there are 3 rings, and right here there was a hole. And Matsumoto was surprised at this point. I don't know if you can show her. At the 4th point, there's a hole, which suggested to me that the micro ball lightning entered into the plastic. So I wrote Matsumoto and told him about this idea that he's making ball lightning. So he started to do ball lightning research. And he started to attend ball lightning conferences because his papers about micro ball lightning were not accepted by by other people. So he couldn't present at the international ICCFs. So he started to present in ball lightning conferences. And so here's a so yeah, basically I think the reason there's these 80-year periods in physics is because there are 3 steps, 3 generations are required for one theory. First, there's someone has to develop the theory. So, for example, Einstein. Someone has to initially conceptualize the theory. For example, Einstein, right? And somebody has to then develop the theory. So, in the 1930s, 1940s, there was a lot of development of quantum mechanics theory, right? And also the development of relativity theory with theories about black holes around that time. And then there was another crisis period in the 80s and 90s with a lot of experimenters, including Matsumoto and Ken Shoulders. But then, yeah, so it takes 3 generations to develop a theory. And then you can read this. I tried to show how each of these paradigms kind of developed, like that. So because it takes 3 generations, these 3 generations usually do their work within 80 years. And so the first stage is done in 40 years uh, for development. The second stage um, requires about 10 to 20 years, but it requires the experimenters to reach middle age. So all these researchers, Fleischmann and Pons, Derryagan, Matsumoto, they were all in the middle age, like older than 40 when they were doing their experiments. And because it takes maybe 40 years for people to gain education and then to have some training and then to develop their equipment, right? So it takes, by the time they're middle age, they can start to discover anomalies. So Davy discovered that there are heat anomalies, which led to the theory that atoms, when they vibrate, that heat is a vibration of atoms and molecules. That idea came from Davy, and yeah, so that replaced fluids, the idea that heat is a fluid. Faraday introduced line of force theory, which replaced the electrical fluid. And then Einstein started to teach that energy is quantized, right? That there's a quanta of energy. So there it goes. Yeah, energy is quantized. And then when Matsumoto started to produce ring traces that were 80 micrometers wide or 50 micrometers wide, and other kinds of tracks, like I used to call them like ditches in the plastic or ditches in the electrodes. They'll find like grooves, like scratches, right? So they make those markings, and I realized he was making ball lightning. So I told this idea to Ken Shoulders also. I wrote him a letter, and he got interested in Matsumoto's work that way. And Matsumoto got interested in Ken Shoulders' work because I sent Matsumoto wanted copies of Ken Shoulders' patents because Ken Shoulders had patents on his devices, so I sent him copies, photocopies of that. Okay, so I don't know if you can read this, but what does it say? Yeah, yeah, but there's not been much research. Okay, so back in the 1990s, maybe 5 or 6 people were doing experimental research on microplasmoids, Ken Shoulders, Matsumoto, and I found them in George Miley's experiments when I was working with George Miley. I found tracks and markings of ball lightning, but there were very few people. But then, let's see here. Oh, okay, so part of this presentation is about the cause of the Kondratiev wave. So Nikolai Kondratiev was a Russian researcher who lived in the 1920s, 1930s. He introduced this theory that every 50 years, on average, there is a economic depression in the West. And also, so there's an economic cycle. This economic cycle it continues to now, and so there's 2 kinds of depressions. One paradigm shift in physics causes two kinds of depressions. The first depression happens during the Industrial Revolution. They're called Industrial Revolution depressions. So IRD. So I call them IRD. Industrial Revolution depressions happen during the Industrial Revolutions because the old industries die away, and the new industries are very small. And even though they're highly innovative, for example, in the 1970s and 1980s, there was a lot of innovation of computer technology, semiconductors, lasers, and all these different kinds of things, right? And that led to telecommunications, but that we're using now. Like even this computer these concepts were developed in the 1970s and 1980s during the Industrial Revolution. I'm sorry, I'm talking too fast. But okay, so there was one, yeah, that was one kind of industrial revolution. And then 30 years after, when the industries begin to develop and mature, there's a great surge of productivity, a great labor productivity increase. And so this labor productivity increase causes people to be unemployed because machinery, automation, replaces the human labor. And so when people cannot work, they cannot have the money to pay for their houses or pay for food or anything or something like that. So then there's a depression, another kind of depression starts, like it happened in the 1930s. So you can see the 2 kinds of depressions here. The IRD and the technological acceleration depressions and the industrial revolution depressions. We just went through technological acceleration depression that started in 2008. But because of the American economy, because the US government can print trillions and trillions of dollars, and because everybody was using the American currency, right? Everybody was using the American dollar. So no matter what the American government did, no matter if they make 30 trillion or 40 trillion dollars, because so many people use it, so many billions of people use the dollar, they they can somehow pay for everything in the U.S. is being paid for. Much of it is being paid for simply by borrowing money, and so there's major problems with too much debt. So okay, so here are some anomalies. Takamatsu Matsumoto found these anomalies, and then you can read that. And so here's a chart I made where I showed the 2 different kinds of depressions, right? The technological acceleration depressions are here, here, and here. 1815, 1950, and we're still in this area. Technological acceleration right here. Oh, no, 1830, yeah, 1830, 1930s, and now we're still in this area in 2020s of a depression era. And then there's, let's see, okay, so now there is a super high debt in the U.S. Oh, here, I'll try to show you a chart. So yeah, the national debt is $3 trillion, which is a lot of money. And then the total debt is about $37 trillion. Um, and every year now, the debt is increasing by $3 to $4 trillion. So this is how the American economy operates. We operate, the government makes money, the government gives the money to people, and most Americans are on some kind of government aid. We get aid for food, aid for our medical care, direct money is given to our bank accounts, all this. So, okay. And then money is given to industry to operate, money is given to the government to operate. So here's okay, so here's the interest of the national debt and how it's increasing. So the reason there isn't a world depression right now is because of so much American money, and not just American money, but also in Europe and in Asia, everybody is just having all the governments are being operated on debt, and so here. So here's the interest rate increase. Um, so in the last 5 years, it's doubled. So now the American government has to pay more than $1 trillion as interest payment every year. So yeah, we're in a depression area. So I think I came to the end of this. What time is it here? I don't. Probably this is not. I don't know if there's any economists watching us right now. Um, I published an article in a Russian journal about 2 years ago called Social Studies. I mean, it's called The Long Waves. So you can look it up. There's a Russian journal that published a long article about this, and another article um, was I showed the. This was published in an American magazine. Yeah, this one, journal.cycles.org, issue this one. You can find this online, and you can find the other one online too, or you can find it through my website. So yeah, mainly I just wanted to say that right now we're in a time in physics where um, because of so much opposition and not enough people studying microplasmoids, there's not much evidence. So over the last 30 years, I started researching in 1992. Um, there's a lot of research, very good research by Ken Shoulders and Matsumoto. Then they died, right? They got old and they retired and died. Then the Russians started to do the research, but they replicated much of what Matsumoto and Ken Shoulders did. Um, and then they actually introduced some new things. Like, for example, for some reason, I call them zigzag or caterpillar traces are very common in Russian research. And Ken Shoulders also saw those, but he usually found rings. Like in my next presentation, I'll show what kind of rings that Ken Shoulder usually found. And I'm wondering, why is there a difference? It could be that Ken Shoulder's equipment basically, for some reason usually produce that kind of a mark. And when Russians do it, maybe for some reason your configuration of equipment is making more of these zigzag tracks. And so I don't understand why. But I do think it's the same thing. I don't think what what Russians call strange radiation is different than what Matsumoto and Ken Shoulders studied. Um, but this ball lightning is a very, very amazing and really astounding kind of thing. It has so many shapes and it's so many configurations of like for example when they make groups they can make like rings or they can make all kinds of geometrical shapes or they make sometimes they just form a chain, like a straight chain, and you can see a chain flying through the air. um, so I've seen ball lightning about 3 times in my life. And Okay, so yeah, but basically, except for these observations and except for some research that Russians are doing that is very interesting but needs to be replicated. There has to be replication for me to understand what's happening more clearly. And people have to write good scientific articles. But in our field, there's much secrecy. Usually, for example, right now, Lutz Geithner is doing experiments in Europe, but they don't talk about it. They, you can't find any article about their experiments. They're keeping it secret for some reason. And a lot of times, maybe this is due to they want to have a patent, right? So as long as people are doing secret experiments and are not publishing good articles, it's hard for me to know what's going on because I need to see that the same thing is replicated by other people to know if something is a fact. If something is a fact, then you can like start to develop the theory of these plasmoids. But right now, we know they exist, we know how they behave. You can conceptualize them as electricity or something like this, or people have tried to say, yeah, there are different configurations of how ions and electrons and everything configure themselves to make these plasmoids. But this is all speculation until much more experimentation is done. But we live in a world where maybe there's about maybe 10 groups of people doing research right now on these, experimental research. And it's simply not enough evidence, I think. During during the 1930s, 1920s, quantum mechanics was accepted by everybody. It became the standard paradigm in physics. But now, this little paradigm of plasmoids is just almost unknown to the world. So we don't have enough money and enough equipment to study these in the way they need to be studied to understand them. Because it'd be good to understand what their effect of plasmoids is on gravity or is on time. Because there is some kind of connection because of gravitational effects that people have seen with very, very big ball lightning and very, very big tornadoes. Um, there's gravitational effects. I mean, people feel like they're being raised or drawn, but it's like some kind of force is picking them up. And so, yeah, but all this stuff needs to be researched, and so that's my yeah. So it may be if this field can continue to develop, uh, maybe yeah, young people would be interested. It has to be young people interested, because only young people have minds that are fresh enough and to be able to to make new theory. In the history of science, it's usually young people who make the new theories and who develop each paradigm. And they, but the problem in America is no young people know anything about ball lightning. It's a field that nobody. I know this because I talk to graduate students and undergrads in physics. They don't know anything about what I'm talking about, and so this field is pretty much operating at like I don't know. It's a very strange field to be in right now. Okay, and then maybe if the field can develop more by the 1860s, there could be a start of another industrial revolution based on ball lightning and plasmoids and what we're working on, transmutation devices, right? But it hasn't happened. So okay, so that's the first presentation, and I'm going to show you my next one now.
Okay, Edward.
Yeah.
Let's make some interruption. Maybe somebody Russians would like to put some questions on that part of your presentation. And
Okay.
now I want to ask for my auditorium in Russian. Just a moment. Друзья, значит, вот он закончил первую часть, вот потратил на это 45 минут, даже чуть больше, почти 50 минут. Может быть, у кого-то есть какие-то вопросы, попробуйте их задать на английском. Вот для того, чтобы ну, как-то начать, вот можно, во-первых, поднимать руки, да, поднимать руки, если кто-то хочет спросить. Можно поднимать руки. Ну вот я для начала я задам сам вопрос. Вот я вижу, Анатолий Климов поднял, но Толь, я Сначала я тут два вопроса сейчас задам, и потом, может быть, еще, кроме тебя, еще кто-то захочет. Итак, Эд, two person would like to put your questions. First, это me, and
Okay.
second, это Анатолий Климов. And I ask you, I have two questions. First question. Idea, it's for me personally, the question is, for me personally, the idea of three generation to solve some scientific problems, to solve some, to change scientific paradigm into industrial revolution, it's a relatively new idea from my viewpoint. And the question is it your personal idea, or you have see some idea in some discussion or in some literature? This is first.
Yeah, it's actually, yeah, it's my personal idea. I think Jesus Christ actually gave me this idea because I prayed a lot. Back in the 1980s, I was trying to understand why are there Kondratiev waves, and then this idea, yeah, the idea that every 80 years there is a paradigm shift is a new idea. Yeah, from the
Окей,
19,
you gave your answer. Thank you. Друзья, я спросил, вот для русской аудитории я скажу, я спросил, вот эта идея о трех поколениях для того, чтобы парадигма научная сменилась и прошла научно-техническая революция, это персональная идея Эдварда, или он где-то это уже видел и просто развил ее как-то вот в нашем докладе? Он отвечает, что это его собственная идея. Вот это очень интересно. Мне кажется, это очень важно и что-то похоже на правду. И я сейчас задам ему второй вопрос. Ed, and my second and last question. Fifth meta statement is it your idea, and what year you born this idea?
yeah, it's my idea also. So in 1992, I realized, yeah, I mean, like, actually, I give the glory to God. I think God gave me this idea of micro ball lightning because nobody believed in that. And then when I thought about it a lot in 1992, I started to realize how small can ball lightning be? I was thinking, okay, if they're 50 micrometers wide, 1 micrometer wide, can they be much smaller? Can they just be the size of one atom, right? And then I started to realize in early 1990s, yeah, that there's another kind of matter that atoms, the regular atoms like solid and plasma, like that, those kinds of atoms can convert to this other state of fifth state. Yeah, so it's my idea too.
Окей, thanks. Друзья, значит, вот я перевожу, что я спросил, и чего там, как я понял, что он ответил. Значит, я спросил, вот это пятое состояние вещества, о котором он сегодня говорил, это, значит, его идея, и когда она у него появилась. Он ответил, что это его идея, и она у него возникла в 92 году. По сути дела, вот он эту идею о пятом состоянии вещества, вот, ну, кроме вот 4, которые как бы в физике были известны, 4 это плазма, вот 5 состояние вещества, он его относит вот к шаровым молниям и к плазмоидам. Вот, в 92 году вот он начал эту идею как бы двигать. То есть довольно давно уже, по сути дела, 32 года тому назад. Значит, окей, Эд, I give the floor to Анатолий Климов. Толь, твой вопрос, пожалуйста.
Thank you, Edward. Very important for me to meet you in our workshop, our webinar. I see you the first time. And my question concerning, continue the question of the Валерий Зателепин concerning to the fifth state of matter. The first who give the name plasmoid was Bostik. Do you know?
Right, right.
But he believed that magnetic field, magnetic forces inside of this plasmoid is comparatively strong compared to the Coulomb forces. Magnetic field, magnetic forces very important for the structure of the plasmoid. Bostic believed in this hypothesis, but what the main idea to use this name from yourself, from you? It's my first question. And the second question...
Давай по очереди. Сначала первый, потом второй. Так. Edward, please answer on first question.
Anatoly Klimov is right that Winston Bostick pioneered this field of plasmoids in the 1950s, 60s, 70s. In 1970s, he started to work with Nardi, and and his theory, because I've read his theoretical papers, was about magnetic fields. And I think Anatoly was asking me, why do I use this word? Because I use the word because the only other word I can use is ball lightning, but ball lightning is too long. And I mean, and it's also, ball lightning is only one type of this kind of plasmoid material. Because ball lightning is what we see in the sky, right? When people say ball lightning, they're talking about an atmospheric ball lightning. They're not talking about microscopic objects that are inside of other materials. So I just use the word plasmoid because it's a very, very good name. It just, you have to redefine, instead of thinking about instead of trying to theorize about the structure of a plasmoid as held together by magnetic fields, the way Winston Bostick understood it. Basically, you have to just, the way I understand a plasmoid, it's I never really think about a plasmoid is contained by a magnetic field. Ken Shoulders, who continued this research from Winston Bostick, if you read Ken Shoulders' book, and you can find his book online, he talks about how he knew Winston Bostick, he knew other people. He was quite active in physics in the 1970s and 1980s. So his idea is somehow electrons clump together, but he didn't know how. So my ideas, I guess, are kind of closer to that. I don't know how. I really we don't really understand the structure of a microplasmoid or a ball lightning. We don't understand this fifth state, even though many people have, not many, a group of people have tried to understand it. I still think there is not enough evidence. We can't examine the inner structure of a microplasmoid yet. And until we can do this, all we can do is make them most of the time. And then we find there's markings, and then we find there's transportation caused by these little micro ball lightning, but we don't know, we really don't know much about this state. So yeah, I'm sorry I took too long to understand.
Толя, подожди секундочку. Ed, may I ask you to use 2-3 minutes for answer? Not very...
Okay.
Because time very, we have limited time. Толь, пожалуйста, переведи на русский свой вопрос для нашей аудитории и комментарий к своему вопросу и к его ответу.
Я спросил Эдварда, значит, вот, что он вкладывает в понятие плазмоид и как соотносится его понятие плазмоида с первым, кто дал такое название, это ученый американский Бостик. Ну, я понял из его ответа, что, так сказать, ну, ему нравится это имя, надо было называть Микро-Шаровой Молнии, это большое имя, он назвал его плазмоид, так сказать, ну, красивое слово. Никакого отношения к Бостику он не имеет. Вот, значит, my second question concerning to the another very key person in the Russia, it's Nobel Prize winner Петр Капица. Do you know Петр Капица, Эдвард?
Yeah, Kapitsa. Yeah, and so
Капица,
yeah.
Капица, Капица.
I'd say Kapitsa.
And he was the second scientist who used this word, this name, plasmoid.
This term.
But comparing with the Matsumoto, it's he used electrodeless, without electrode. Discharge created a high frequency microwave plasmoid, And so this very interesting interaction of the plasmoid with materials, different materials, is typical for the electrical discharge with the electrode system. It's a trace of the cathode drop, cathode dot in the surface of the cathode or anode.
Mhm.
And so, what's the difference? Do you differ? Can you explain the difference between the Matsumoto approach and Kapitsa approach? Absolutely different approaches.
Yeah,
But plasmoid the same.
right. The plasmoids are it's very confusing. I know what you mean. Okay, I've read very little about Kapitsa. That's how I mean I knew that he did nuclear research, right, in Russia. And I know that he studied plasmoids, but I am not really aware of the kinds of tracks and markings he made. So if you could send me, or if I could find some like an article that shows these pictures of what kind of markings he made. The difference here, okay, here in America, if you watch YouTube, there's people making microwave. They use a microwave oven, like these little microwave ovens to make plasmoids. But it seems to me that these plasmoids are different. So I think in nature, there's another kind of object that's it's not in the fifth state. It's more like a plasma that is contained, but somehow self-contained. But they're not a fifth state of matter because you can't find transmutation. Klima, did Kapitsa ever announce that he found transmutation when he did the experiments?
Yes, he has a transmutation from the deuterium to the helium.
Okay, but not from not palladium to silver to
No,
gold.
no, not at all. It's electrodeless discharge,
Right.
microwave discharge. It's without electrode.
Yeah, I understand. It's similar to Winston Bostick was also doing research on making deuterium to helium or something like this, but using electrical discharge. But it doesn't seem to be the same thing to me. It's I believe that there's some relationship, but these ball lightning is a very, very strange thing because the behavior. First of all, they can last so long, right? I mean, in materials, people are finding, for example, John Dash uh, was showing these filaments continue to grow for months. Like if you do an experiment and you put the components away after the experiment for months. You'll still find reactions happening. So that's the fifth state of matter. This weird stuff that's happening without any energy input. It shows there's a state inside this material or on the surface, right? So I think Savatamova also talked about this, and also when Ruthkweb and other people are finding that components continue to emit these microball lightning or microplasmoids, they continue to emit them maybe 1 month or 2 years later, right? Something is inside there that's doing it. So that's what has to be researched. To stay.
Ed, sorry, it's not an answer. It's a discussion about the question.
Okay.
Let's finalize this.
Okay, let's do it.
Discuss. Okay, thank you. Толь, ну ты второй вопрос тоже
Ну,
по-русски.
я спросил его, все-таки знает ли, что вторым, значит, известным ученым, который использовал слово «плазмоид», является Петр Капица, Нобелевский лауреат в России. И вот он-то как раз пытался шаровую молнию воссоздать с помощью микроволнового разряда. Я говорю, там нету, значит, палладия, нету электродов. И никаких тогда Мацумото тут за уши притянут, так сказать. И никакого Леннера, так сказать, вот на электродах, по крайней мере, нету. И вот он начал здесь путаться, так сказать, вот ему хотелось бы, вот, чтобы была реакция, так сказать, и обязательно притянуть за уши Леннер. Вот что он хочет, так сказать. Четкого понятия нет у него. Я ему говорю, что на самом деле Капица видел трансмутацию, из дейтерия появлялся гелий. Значит, ну, это трансмутация, да не та. Ну, в общем, вот то, что пока путаница полная. Ну, давайте послушаем дальше.
Толь, понятно, спасибо. Значит, я просто в оправдание Эдварда хочу сказать, что этот доклад, вот второй вопрос Анатолия Климова, он шире гораздо, скорее относится ко второму докладу, чем к первому. Толь, спасибо. И last question from Bob Grenier, but Bob, a lot of time we spent for first part of presentation, short question and add short answer.
All right, short answers to try.
Bob, your floor.
Ed, are you aware that I have all the original material from Matsumoto?
Yes, because you visited him, I know.
I have everything he ever did.
Wow, cool.
So I can improve all of your media.
Okay.
But I can answer both your question and Anatoly Klimov's, but I will do that discussion at the end.
All right. That sounds good.
Bob, your answer is your answer. Today Edward is main presentation.
Yeah. Okay, so the next this one is actually probably a lot more interesting to you, and the problem is I have to find it. Let's see here.
You may switch off your presentation. Next presentation, please.
Yeah, next presentation.
Bob, sorry, I interrupted you.
No, yeah, I understand. Yeah, actually,
on discussion, Bob. On discussion, you may say some words about that. Ed, continue.
What I'm trying to do is find my thing. Okay, so I sent it to PDF. Okay, this is also a bilingual one, so this should help you. I hope if I can open this. There it goes. All right. Now I'll switch it back on here if I can. How do I do this? Sorry about this. I'm trying to find, where is the switch on button here? No, not here. So
не может найти свою ту самую презентацию. Ed, take into account that you will have only 30 minutes for second presentation.
Okay. Sorry about this. Okay, so no, not this one.
I explained to you that first you should run second presentation on your computer.
Yeah, there it goes.
Okay. You find it. Okay, thank you.
Okay. So here, okay. So what makes it? No.
This is first, not second.
Wrong one. Here, okay, how did this come up? So there should be a second one here. I'm sorry about this.
You switch on this same presentation as you told.
Yeah, it's like I know it's here. I just this one? Nope. Not. Can you see what I'm showing you? Is this
You show first presentation. You should show us second presentation, not first, second.
Yeah.
You should switch off this first, switch off, and switch on second.
Okay, let's try this again. First I have to open it though. Okay, file. Okay, PDF. Not this one. No.
On the very beginning of this webinar, you switch it on. On the very beginning, it was the right presentation. It was second. On the very beginning.
Yeah, at the very beginning, it's why can't I find it? But this isn't the one that's been. No, I had a. Yeah, here it is. Ah, I found it. Okay, so this one. Okay, good. Okay, now I share this here. Oh, here. Oh,
Демоны, однако.
the computer. Why?
Друзья, подождите немножко, он ищет, что-то не может найти.
Wow, so long.
Ну,
Okay. Wow, my computer is really acting weird. It's like open the file, right? It's a PDF. I sent it to you actually.
Bob, Ed, maybe I do that, and you will continue with my presentation.
Sounds good.
Is it okay?
Yeah, sounds great. Yeah, we'll just say next one. That's where I'll go faster too. Okay. All right. So if you could, but I have to see it. It's really strange. My computer isn't actually opening my file here. Not sure why. So if you can open yours and show it, and then
I'll try to open this. It's very strange. I can do that. You can't. Yeah, I will try to do that. Just a moment.
Why is this? It's like my computer is freezing or something. Open. Oh, it doesn't work. How come it's not working? Yeah, it's like it's so slow. Oh, I don't know.
Скажите мне кто-нибудь, видна презентация сейчас?
Да, видна.
Да, хорошо видно.
Yeah, there it goes. Thank you. All right, so this is the work.
Пожалуйста, Ed, continue please and give me to change the slide. Start your presentation, please.
Start mine.
Your speech.
All right. Let's see here. How would I stop mine here? Like this?
It's Russian version of your slides.
Yeah, right, Russian. Well, actually, there's a Russian-English version. It might be good.
Он не может по-русски ориентироваться, потому что он прислал вот русскую, а по ней ориентироваться не может. Ed, could you find your presentation on your computer?
Yeah, I'm trying.
Or you couldn't?
I have different I'm having a very weird thing going on. I don't understand why my. Okay, maybe this will work. Okay, I think I just called it up. So what I have to do is go to
Валерий
Zoom.
Николаевич, может быть, вам имеет смысл ему сбросить название, которое он прислал, а он через поисковик в своем компьютере ее найдет.
Евгений,
I have it.
я с ним работал уже не первый раз. Это все это очень и очень сложно. Давай без советов. Значит, спасибо. Эд,
Yes.
once again, could you switch on or you couldn't? It's very strange. In the beginning, you showed us this presentation. Now you can't. Is
this good?
This is good, yeah, but it's very, very big. Oh, okay. This is right presentation. Okay, Yes, it's right. Continue, please.
Okay.
Only 30 minutes.
Yeah, we only have a few minutes. Okay, so here's Matsumoto's original tracks from the 1995. He called it ball lightning marks, micro ball lightning. This is Uruskriv's right on the right? And then this is a picture of ball lightning going through the window. Yeah, interesting. You can see there's a tail. So I'm in these slides. For some reason I'm interested in tails. What's causing this tail that makes it look like a comet? And is it because like comets are plasmoids too? You know, that's the question I have actually. So plasmoids are an interesting structure of matter and energy that's outside of quantum mechanics. There's no way you're going to, even though Lutz and others are trying to explain this by quantum mechanics, you can't. The reason you can't is because things are going on that quantum mechanics cannot explain, which is why there has to be a paradigm shift. So, okay, so here's a picture of these plasmoids that I'm trying to say that they're everywhere. They come out of volcanoes, and you find them in the sky, like you can find them inside of clouds. So there was an American researcher named Herbert Jones, I think, who talked about how he sees very, very big lights inside of clouds. And often, well, not often, but sometimes these big lights turn into tornadoes. So, that's an example of atmospheric ball lightning and how it causes weather phenomena. Okay, so here it talks about big ball lightning comes from volcanoes, and Egon Bach wrote about this in the 1990s. I don't know what happened to him. I tried to find out, was he alive? This was back in 1990s. I wanted to write him, but I could never find him. So maybe he died. So, but he wrote a good book. It's called UFOs from the Volcanoes. So here is a Tom Warner video, one frame where he shows that ball lightning at the beginning of every lightning stroke, if you take a very, very slow motion video, you'll see a ball going through the sky. Before the lightning stroke, there's a ball. And the videos of Tom Warner show this. But I don't know why this area of physics isn't studied more. It's very interesting that lightning is created by ball lightning. And we don't understand that. So, okay. So you can see that in this frame, you start to see a tail, right? There's a ball moving across the sky, and then you start to see a tail following the ball. But actually, this is moving so fast, you can't see it happen. What you see happen is then after the ball lightning moves across the sky, then the whole trail of the ball lightning lights up. So then you have lightning. So that's so this is a picture of a big ball lightning mark. there's a lot of these. Other ball lightning researchers, such as Otsuki, he was Japanese, and Ofuruton. There were two Japanese researchers who, I think Matsumoto knew them actually. So they found ring markings in the grass or, you know, someplace. And then to the right, there's these rings, and people would call those in England crop circles or something like that. But they look very similar to this, right? So this is by Matsumoto. So so it shows that what we're dealing with is everywhere. It's not just, you know, microscopic. It can be very big. So this is Ken Schilder's original tracks. On the left, you see what he called an EV chain, right? Then Matsumoto, if I remember correctly, made the next one, which shows that the chain somehow broke. And so it's really interesting, or that's how I interpret that. And the next one is by Matsumoto also. And it shows like the third one is from electrode tracks. Then I put these all together. You can see that, yeah, Matsumoto also found these long lines, right? And it shows that somehow the rings made that, right? So as if it's like a tornado going across the ground. And this is kind of similar to this one by Viau. I don't know how to say his name. He's French. Is similar to that one, that second one, right? Okay, so and then this one, what did I put? Okay, anyway, it's okay. So this is by Baranov. Yeah, I really like these pictures. They're so beautiful. They're so clear also, you know. And this is in comparison to what Matsumoto made on electrodes, right? And then here's some more by Ken Schilder's. I'm just showing different kinds of rings here. Savatomova, Ken Schilder's, Matsumoto. And then, yeah, so here, so the Savatomova, Ken Schilder's, and all that. And they're so interesting. There's so many shapes to this. It's like amazing, right? I don't know who made this one. Baranov, yeah. So I think all of you are familiar with this, right? I mean, you study his papers. This is by, what is this? Okay, what is this? I think, did Baranov make this? Maybe, yeah. Yeah, they leave deposits. So Matsumoto started to find all kinds of deposit marks, including, they're called hexagons. And that's interesting too. Why do they leave hexagons? So, and I'm trying to go fast. This is Ken Schilder's holes. So one for this fifth state of matter, they're so okay, amazing. One kind of, sometimes they can switch states. One state will make a hole, like just like that. This is a tunnel showed by Jim Egley. So it was in he wrote a book called Hungarian Ball Lightning Observations. So that's from that book. This one on the right is by, is it Shoulders? No, it's by Svatomova. Yeah, and they're so powerful. This is metal. On the right, it's hard metal, and still is able to make kinds of grooves. I call them grooves or scratches or something like that. So, so yeah, Svatomova, Davao, and they make tunnels. So, okay, in Russia, a lot of people, for some reason, are only focusing on surface markings, but they also make tunnel markings. They they can go under the surface, and then they make tunnels, and this is why sometimes when I read Russian papers, I think they're not really understanding how different these are. It's not like a particle of some kind of dust is making this. Whatever is doing these kind of things can make a tunnel, and these tunnels can be very long under the surface of materials, right? Under metal, under glass. And so, yeah, so here's some markings by Priakin where he talked about their effect on plants, right? and so some of these caterpillar marks are on glass, and some are on X-ray film for Priakin, and then here's okay, showed a long time ago, is that when one of these objects, microball lightning or a microplasmoid, contacts glass, somehow the glass, it seems like it melts, but it doesn't actually melt, because Ken Childress has always said he can never detect any heat. Somehow it turns the atoms into something like a superfluid, but it's not due to heat. And that's the other concept that when I read some Russian articles, they often say, well, they must have heated the material in some way, but it doesn't actually heat the material. It just makes it move. And, you know, it somehow turns the atoms into a different state. And then in this different state, like they start to move in very strange ways like that. So, okay, so that, and yeah, so he called them EVs. So, and this is on, this is actually a very similar thing. So see that, and then see how Mars, right? On Mars, you can find these objects also. This kinds of craters and that kind of, it looks very similar to what Ken Childress made, right? So yeah, these are huge. These domes or whatever they are like in these craters are kilometers wide or 100 kilometers wide, something like that. So they take them from the spacecraft pictures, you know. And okay, so this is a picture of, it was found over Tijuana. This big ring formation was over Tijuana. So someone took a picture of this. And see how it's very similar to the ring cluster, the beat chain of Ken Childress there on this side. So I think it's pretty amazing how they act. I really don't understand. Actually, I do. Maybe I understand. A long time ago, I met Ken Childress, and he was trying to explain when the plasmoid ring hits the surface, it'll leave a ring track similar to some of these kind of you don't see individual pits, which is something like that, you know, like what Matsumoto showed. You know, you don't see individual pits there. And this, he was talking about Bostic's experiments. They didn't find individual pits. He was the first to show, because he said, if you read his book, he started to fine tune his equipment. So he left behind all the other cloud of, I guess it's electrons or a cloud of plasma. And these little inner pits, which he calls, so in his, the plasmoid is kind of the whole object, but inside of a plasmoid you have EVs. So that's what he would talk about it. So the EV, those are EV pit marks, right, on the right. So those I call them microball lightning pit marks, because I identify the anomalous object as the material in the fifth state. The cloud of other material could be a plasma that surrounds the thing, right? And that's why you don't see individual. Sometimes when it's a ball lightning, what you just see is just ball. You don't see a configuration of objects in a circle, right, or something, or in a sphere. So then so here's what did I write here? Oh yeah, and then John Dash. So I started in the 1990s. Started thinking, how long can this material last? Is it just for a few seconds or a few minutes? When I started to understand about tornadoes, that they can last, you know, a long time, like an hour or 2 hours, like that, hour and a half or something. Then I said, how long can the material last? So, and for the first time in the early 1990s, I thought, when I read Ken Childress' paper in 1995 in Fusion Technology, where he showed pictures like this. Yeah, he started talking about fibers and things like this growing, right? So grow over a period of and these fibers change shape, and they were just sitting there by themselves. And then I said, oh, that's the first evidence I saw that there's an actual state of material that continues to grow by themselves. And then there's isotopic change, right? He doesn't record that there's elemental change, but he does try to show there's isotopic change, if I remember correctly. And this is by these more crystal formations, or not crystals, and by in 2013. And okay, is a picture of a kind of a. It would look more like a ball if he hadn't pictured this. You can imagine there could be a cloud surrounding this, and then it would be look like a sphere. But Bogdanovich was able to show the individual micro. And the one on the left is also by Bogdanovich, right? And that one was moving very slowly on the surface for a few millimeters every second, he said. This is also Bogdanovich, and this is starting to show that there's two black state. So in Ken Shoulders experiments and also in natural ball lightning, you can find that they change shape. Change state. So the state of matter, the fifth state of matter is in itself has states, the black state and the white state. And individual ball lightning can change back and forth between these states. And when the state is white, then they're very active, and they can cause holes and tunnels and electrical shocks, and they can explode. But when the state is dark, in the black state, then they're very, very difficult to detect, and they can go through materials, glass or any other material, as if without any interaction with the material, or very, very little interaction. So here's the states. You can see the ring that the black ring is backlit by the bright light behind it, right? So that's why you can see a ring there. You can see sort of outline of the object, but you can't actually see the object. The object is black, right? Because it's in the black state. But I believe that these black objects can change state to a white state, and then they can change back. So Egon Bach wrote a book where he actually showed pictures of very, very big ball lightning that were in a chain around a volcano. How they for a while they're white, then they turn dark, then they white, then they turn dark. I think that's state shift. And the other idea about this ball lightning is how they have such sharp turns with any acceleration normal in the way we under and acceleration. An object has to slow down if it's going to make a turn. Like, for example, a plane can't just go one direction and then take a sharp turn to the right. It's impossible. There has to be a curvature, or there has to be a deceleration. Like a helicopter maybe stop and then turn 100. And is also talked about how these don't show any acceleration or deceleration when they move, and he was to use this frame as his evidence. And there's other pictures like. So he says this because you can see they're turning, but there's no brightening at the corners. I know this because I talked to him. I talked to him several times. So he showed me this picture, and he talked about it, I think. Or anyway, he talked about these kinds of pictures. It's the same UFOs or a big ball lightning. You'll see people say they make such sharp and very fast turns, and it seems impossible with no curvature in the turn. Okay, so these are like, yeah, not really well understood things, but and then they have physical effects. So I liked this paper by Pyakin and also by Rutsgrev because they actually showed physical evidence, and I thought it was a good paper. So I wrote a paper about this, and I think I put the link. Yeah, there it is, Infinite Energy. And you can go to the website, infiniteenergy.com, and look up the 2024 article in, I think, March or February or March. And it just talk about, if you're doing experiments, please be careful about the effects And so, okay, thank you. So it's finished. Now you can ask if you want.
Okay. Thank you, Edward and friends. Друзья, значит, пожалуйста, ваши вопросы Эдварду. Значит, ну, если нет вопросов вот в настоящий момент, я тогда попробую задать. У меня есть,
Вопросы есть.
наверное, один или два вопроса. Ну, поднимайте руки, пожалуйста, если кто-то хочет задать вопрос. Вопросы на английском, а вот выступать можно будет уже по-русски. Значит, ну, я тоже все-таки задам вопрос Эдварду. Эд, you, as I understood you, you talked that Linear's lightning is a movement of ball lightning through the atmosphere. Is it right or not? Once again, linear lightning is a movement of ball lightning. Is it right or not?
Right. It's a path. It's okay. So yeah, actually it was Ken Shoulders who I think introduced this. I didn't realize it.
First of all, yes or no? After that
explanation. Yes, basically, yes.
Окей, thank you. Значит, друзья, мой вопрос был, если я правильно понял, значит, вот презентацию, то по мнению Эдварда Льюиса, линейная молния является проявлением такого вот хитрого движения шаровой молнии. Я спросил, так ли это? И он ответил, да, это его точка зрения. Окей, значит, я не имею больше вопросов, и подняли
Да елки-палки, что оно...
Два человека. Ну, Евгений, я вижу, что вы поднимали руку. Не волнуйтесь, я дам вам слово. Толь, пожалуйста, тебе вопрос. Друзья, задаем вопрос на английском, а потом комментируем по-русски, что хотели спросить и чего он, по вашему мнению, там ответил. Толь, давай. Включи микрофон. Толь, включи микрофон.
Edward, you told us about fifth meta state, and definition of this name is absent in your presentation. What do you think about exact, correct definition of this name plasmoid? For example, plasma definition plasma is the mixture of the charged particles. It's well-known definition. And what means plasmoid according to your presentation, according to your opinion?
Yeah, a plasmoid in the fifth state. You know, there's different kinds of plasmoids. I mean, like if you read books about ball lightning, there's other types of plasma that are in nature that you can see that retain their shape, right? So it's a plasmoid, but the fifth state of plasmoid, like the plasmoids in the fifth state are some kind of structure of electricity, and somehow the electricity retains their shape, and inside of this, there may, as far as I know, there may be ions. Like there may be, because nobody can really do any experimental research. We don't know what's inside of a ball lightning. I mean, we assume, okay, if atoms are coming at us, and then you can assume like the way that some theorists such as Geithner and Lutz Geithner and Mishinsky and others are saying, inside of say,
Edward, do you have a short definition? Oh, you don't have at that moment.
There's no. Yeah, okay, some kind of it's matter. My basic definition is that's less
Sorry, very big, very worst connection at that moment. Connection is very bad.
Yeah,
at that
but my
moment. Continue,
explanation-
continue, please, to several last sentences of your answer. Continue, repeat, please. Repeat, please.
Yes.
No, bad connection at that moment.
So, a plasmoid that's in the fifth state of matter is basically electricity, somehow bound together, somehow that doesn't dissipate, and then maybe it has ions inside it, but there's no experimental evidence that it has ions in it. We just assume they have ions, and I actually don't assume that myself. If you believe in quantum mechanics, you're going to have to assume that, yeah, there's ions inside it, inside of this kind of matter. But yeah, there's somehow, I don't know, it's another state of material, I guess. Was that, so I say that the atoms themselves are in a different state. I conceptualize it as atoms in a different state. So just like, okay, so an atom in solid acts one way, an atom when it's in a gas, different way. So the same material acts very in different states, right? The atom.
Sorry. No short definition you have that moment. Толь.
Yeah, no short definition.
Пожалуйста. No short definition.
Yeah, no.
Пожалуйста.
Yeah.
Let's stop your explanation. Толь, твой вопрос прокомментируй, пожалуйста, на русском и ответ.
Я спросил, значит, вот у Эдварда, значит, есть ли, так сказать, определение вот пятого состояния вещества, которое он назвал плазмоид? Ну, по аналогии, вот плазма есть, ну что, как нас учили, смесь там заряженных частиц в пространстве. Значит, ну вот он начал путаться, и, значит, ну, вывод такой, что сейчас определения четкого нету, но вот он считает, что это электричество, ну а дальше кванты играют важную роль, набор звуков, короче говоря.
Ага, спасибо. Толь, еще есть вопросы?
Все.
Спасибо. Second answer from Bob Grenier. Bob, short question and short answer. Bob, your floor.
I'm going to wait to the discussion, so.
You don't have questions, yeah?
No.
Okay, that's for discussions. Okay, Евгений, вопрос.
Thank you very much for your very interesting report. This first. And you know about works Vachayev and Ivanov and about their reactor, which was built in Magnitogorsk in the South Ural Mountains. This reactor gives metals and
Евгений, вопрос, Евгений, стоп. Вопрос был понятен. Ed, your answer.
You know about, yes.
Do you know about Vachayev and Ivanov? Ed, where are you?
Связь плохая.
Он исчез.
Связь плохая.
Его нету связи.
Он отключился, вообще его нету.
Да, у него там какая-то такая плохая связь была, что он, по-видимому, пропал. Друзья, тогда давайте начнем, уже мы довольно много говорим, значит, давайте начнем дискуссию. Ну вот Боб Гренье первый поднял руку. Боб, can you switch on subtitles of your answer or of your discussion in Russian subtitles on your screen?
Unfortunately, I can't because it's not in a presentation.
Okay. Please talk in orally, and maybe we will try to understand what you would like to say shortly and clearly.
Can I share my screen?
Yes, you can.
Okay.
По-моему, это if you would like to,
Is that sharing? Can you see?
Yes.
Okay. So the first question I think that Anatoly had was, what is the difference between Kapitsa's ball lightning and the micro ball lightning of, say, Ken Shoulders and Dr. Takaaki Matsumoto? I would argue they're largely the same, except one, in the case of Kapitsa, is typically, or in our ultra experiments, is due to resonance. And within resonance, according to Kapitsa's 1950s paper, you get a reflection of the microwave, or in our case, in ultra, the sound wave. And on the antinode, as per Kapitsa, you get a transverse. He says it's parallel with the ground, but we see transverse in our ultra experiments. And around that, you get turbulence. In the case of Kapitsa's ball lightning production, the electromagnetic waves cause ionization. In the case of our ultra experiment, you already have charge separation in the polar molecules, and then they get charge separated when they interact with the aluminium foil. So in both cases, in Kapitsa's, in our sound experiments in water cavitation, it's standing waves or phase conjugated waves, and you get the material, the electrodynamics produced transverse to that. So it's charge separation and shear. In the case of Bogdanovich, and if I pull up some slides on Bogdanovich's work, maybe I can do that here, perhaps. Maybe it's better than this one. Okay, so in Bogdanovich's work, he used a 10,000 amp pulse, and it produces a plasma loop which has magnetic reconnection, and then he fires a minimum of these two. When this happens, the plasma is undergoing extreme hydrodynamic shear colloidally. So it's the same thing going on, it's just going straight to the structure. And then they form tores of tores. So the same thing is going on from a resonance sense in our ultrasound experiments and in microwave experiments. So they produce the same thing. So that is basically charge separation and extreme hydrodynamic shear leads to these formations. The separate question that was presented was about how it forms hexagons. Well, in our experimentation, when you have the ball lightning, and so this is a quantum coherent condensate of Bose-Einstein condensate of atoms, and you can see the regular clustered array, but it's expressing as a hexagon. When you look at Bostic and Nardi's work from 1980s, you can see these multiple ring traces, but if you look inside the traces, they got substructures. They've either got rings that are orthogonal to the main ring or these bulbous areas. Well, we observe this with ball lightning strikes on our fused quartz, and you can see a 6-order structure here, a 4-order structure here, but in this case, you can see these are these kind of round blobs. This is what happens when you just get a strike mark. But when you actually get them manifest into solid objects, they then present themselves in crystal structures because they have to become normal atoms. And this here is a split structure, which is observed by Matsumoto here, this split structure that was referred to by Ed. And you can see this is a segment of that, and I can go into slightly more detail on that here. This is from the archive that we're working on, and this is a different focal depth, and you can see that the split structure is made of substructures. Moreover, when these ring structures break up, here was a ring structure breaking up, so the ring is here, and it has 3 things orbiting around each other, and then one of the 3 things breaks up, and then you have 2 things orbiting around each other.
Can you show that? Can you show that, Bob?
Yeah, so he describes it in his work, but not in his book, as a ring structure that is breaking up here.
Okay. All right.
Okay, and
Yeah.
if you actually go to my recent presentation to the ICMNS group, I can show you here where this is the image that we just looked at, where you see the ring structure breaking up. And here is where we see a coherent matter ball lightning structure breaking up. And so you can see this, but what you're seeing is persistence of vision in the camera trail.
But we don't see it. You haven't put it up.
You don't see it?
Yeah, can you put it up on the screen?
Oh, no, it's on the shared video. Can you see my shared video?
Okay, I see you. I don't see any pictures.
Can anyone see my shared video?
Yes, you can.
Okay, so I don't know why you can't see it, Ed, but it will be on the recording and I can send you these slides later. But essentially, we've got a plasma reactor and we've got a number of traces. And I'm comparing the trace observed by Matsumoto in, I think it was August 1992. It's published in Fusion Technology. And our traces produced in plasma in the reactor. And what you're witnessing is two structures that appear to be orbiting around each other. And you're seeing the persistence of vision of the trail as far as the camera is concerned. And when we combine these together, you get the full length of the trace. And this is actually 1, 2, 3, 4/60th of a second parts of the trace. In this particular case, this is a frozen coherent matter wave beam that is collapsed into a diamond braided structure. This is in a plasma reactor in Holland. This is in a plasma reactor in Canada, and there are 1, 2, 3, 4 segments here of multiple structures orbiting around each other. This is in the Dr. Roish and Amaza cavitator. So what Matsumoto was seeing here and what we are observing here, we see the ball lightning forming and then we see it breaking up. And a more extreme form of that is what you see here, where you see the structure that was in the material that persists for a long time and blowing up. And we witnessed this in cavitated fuel from Dr. Suhas Ralkar in his fuel container appear over a period of time. And so the comparison between Matsumoto's work here and this is very, very striking indeed. So to go back to the broken up structures here, this broken ring trace here is because this is made of substructures, and when the substructures fail, they can open up. And this is an example here showing a full ring that hasn't broken up, and this is showing part of a ring that would have had 48 subsections.
Well,
and here
Bob,
is another.
Bob, could you share that? I mean, I don't think you actually have shared it because we don't see anything.
I think people can see it, but I don't know why you can't see it. I think you're in the browser version rather than the downloaded.
Oh no, I'm actually in the share version. Why am I?
Maybe
Valerie, can you see his pictures? Because I don't see. I just see Bob and I see no pictures.
Maybe it's because you came in afterwards. So I'll stop sharing and start sharing again.
All right.
Try that.
Yeah, that might work.
And you are also sharing something on your screen, so that might be your problem.
Okay. Yeah, maybe I should.
If you unshare your thing, you'll see what I'm showing everyone.
Okay. All right. Wait a minute. Oh, I see that now. Okay.
Right. So just for Ed's benefit, what I'm showing here is Matsumoto's ring trace, where the ring here has partially broken up into 3 substructures. One substructure here leaves, and it leaves 2 substructures coming down here and ending here. And
that's interesting.
And I'm showing here, in our plasma reactor, that we have a ball lightning forms here on the video. You see it. Then it fails and it shoots out 2 orbiting structures that are coming out. And if I join those 4/60th of a second frames together, we end up with a structure that is functionally equivalent to what Matsumoto observed. Moreover, on this particular image, if we go to this presentation, you can see other examples. This is like the work of Anatoly Klimov, where we have a ball lightning that's broken down the bottom here. Okay, and in fact, the ball lightning looks like this. we're able to look through the ball and see into the ball that it's made of substructures, and that those substructures have substructures within them. So this is a wheel within a wheel within a wheel, making the overall ball. And that is the basis of the electrodynamic structure. It's all magnetohydrodynamics. And when these things break up, they let out subquanta. So the track that you observed earlier, borrowing through the material, is effectively one of these structures, where you see mostly on one side the punch hole. The other thing that you said was about things moving around each other. This is 3 frames, and they don't care about the cathode and the cathode is the bottom, the top is the anode. They only care about each other when they're in event horizon. So what these structures have is a non-radiating boundary, which is the spherical part of the ball lightning. And it all comes from an extension of Yakov Zeldovich's work with the work of our good friend and sadly departed Vladimirovich Dubovik. When you get these electrodynamic structures interacting, they produce a non-radiating boundary, which is your boundary of ball lightning. Now, what Matsumoto showed in his book, but it wasn't clear enough, but we can now reveal, is he observed these tores of tores. And in fact, some of his most incredible iterations of showing this, I can show you here. And so this is exactly a replication of what what Bostic saw. And in this case, he actually has 48 subtores. And in the subtores, you have multiple tores within the tor within the tor. So we've got substructures here. That makes one substructure that makes the overall structure. A wheel within a wheel within a wheel.
Okay, Bob, could I ask a question?
What's that?
Okay, where did Matsumoto ever publish any of this?
This is not published. This came out because he told, when I met him before he died, he told my translator in Japan that when Bob gets the materials, he's going to find some very, very interesting things in there. He
never published this.
He never published it because I don't think he realized the significance. He did publish this, but it's not high enough quality on the book, even the remastered book, to be able to observe it. But he does discuss it.
Right,
So
right, yeah.
This is actually in his book. These traces here, these ring traces with substructures within them. Okay?
Yeah, those are very, very good pictures. Yeah.
We're going to be republishing this in full color with remastered images from the original negatives. And if you look here, I've got 142 kilograms of the original materials. And it's spectacular. So, like, for instance, you were saying here about you don't see these traces. Well, here you see an exploded, where is it? Here you see an exploded ball lightning with the substructures coming out. Okay. And when you look at this under the imagery, this is actually a hemispherical pit. And then you see these 2 structures coming out, and they all start to orbit around each other. And then sometimes they break up and split up and go away.
Okay.
But he observed all of this. And also,
that's extremely important, actually.
And here you can see the ball lightning, that's the sphere, and here the orbiting structures around it as they are interacting with the material. And I showed how this was functionally equivalent. And fortunately, I was able to share independent replication of nearly everything he observed before he died, and when I visited him in Japan last year. So it was very fortunate I was able to see him before he passed and be able to show that his work was independently replicated without anyone actually knowing they were replicating his work, if you know what I mean. So I just want to answer all the questions that were asked and so the confusion. So the tail is 3 things. It's a persistence of vision and ejection of captured or synthesized material. So I can show you here. This is in Binjuan Huang's system. So here is something that's being ejected from the magnetic core. And this is 2 titanium discs, largely, and a mostly carbon ejection. Carbon is one of the most products that's observed being ejected. So this is 2 titanium discs, titanium rich. You can see here it's 11.3% by weight. Their structures are hollow, as identified by Sviatomenko. This is in Huang and my analysis. There's titanium structures within, or toroidal structures within the magnetic core. And when this particular magnetic core broke up, like a horse chestnut, it has toroidal structures within it that come into the core. And you see that this is rich in titanium. It's 23% here. And this is the fusion of CO2. The structures are toroidal, but they can become almost spherical in terms of their non-radiating boundary. This is axial hypertoroidal moment. You call it supertoroidal in Russia. I call it fractal toroidal because it makes more sense to me. And this is what we got out of Binger and Huang's system, a yin with a yang, yin, and the yang with a yang. And these two structures are bound. Sometimes they can link together. But inside they have subtors. So these are the things that you see flying out, and they can orbit around each other. Anatoly Klimov has seen this in his plasmatron devices. And when they fail, they eject the synthesized or captured material. And this could be part of the trails that they leave. You see in this instance here, we have one of these large structures. These are the same size at 20 microns as identified by Ken Shoulders. This is the non-radiating boundary of the outer structure. And you can see all of this synthesized material, which is typically stellar synthesis. What I like about this experiment by Binger and Huang is on the copper oxide substrate, it gives a high contrast between stuff that's synthesized and coming out of the structure and stuff that is in the background. Here you can see a structure is completely broken up, but before it did, the substructures inside have braided the synthesized material, which is rich in titanium and carbon bands. In this instance, you see where the material is sucked in to the magnetohydrodynamic structure, and it's so powerful that it can rip copper out of the solid metal. And it does this, I believe, by weakening the electrodynamics of the metal bond. And so the metal falls apart and it's not melting. This is one that's spewing out material. So you can see here, this is the magnetohydrodynamics at play. It's exactly and precisely magnetohydrodynamics. And when you look at the broken substructures, and I haven't changed the scale here, this is 20 microns. This is just moving the microscope. I can overlay here the same structures, 20 microscopes, microns. This is the substructures inside. And you can see here the substructures inside. And this is folding around on itself. This is folding around on itself. And so here is one of the large structures, and it's consuming the the copper as it's crashing into the structure. In this case, on the right, you can see it spewing out the synthesized stellar synthesis of material in a vortical beam coming out. So that, I believe, answers the tail. Now you get tores and spheres because you are seeing substructures, or you're not seeing the full non.
Bob, the auditorium told you that a lot of time you spent for your...
Okay, fine. It's just, I said it was discussion.
Регламент у вас есть какой-то или нет?
Yeah.
В 2 раза длиннее, чем докладчик говорит. Ну, сколько что-то можно.
All right. Yeah, so like I would encourage people to take part in the, if I just stop this and...
Okay, Bob, thank you.
Но материал-то интересный.
Да, Толя, я говорю Никитину, Толь, ты зачем-то включил свою презентацию. Выключи ее сейчас, там красную кнопку нажми наверху. Ты нажимаешь на все кнопки подряд, не думай о чем, что ты делаешь. Пожалуйста, выключи свою презентацию. Красная кнопка наверху. Анатолию Никитину говорю.
Я выключаю, там нет никакой красной кнопки.
Есть, ты ее просто не видишь. Иначе я тебя просто тогда должен выключить, потому что ты экран занял.
Нет, я хочу
зачем ты ее запустил?
Я хочу включил микрофон, чтобы...
Да не надо, ты не микрофон включил, ты презентацию включил.
Боб,
красную кнопку наверху, квадрат такой красный, увидь и нажми на него. Иначе я сейчас тебя вынужден буду выключить. Ты не даешь вести это самое...
Да, выключай меня, я не знаю, как это сделать. Нет у меня
красной. Не знаешь, тогда я тебя, Толь, не обижайся, я тебя сейчас тогда вынужден буду отключить.
Давай я сам выключусь. До свидания.
Ага.
Bob, very interesting presentation. Thank you very much. It's your collection is comprehensive.
I would
Так,
like to say
это самое.
thank you, and I say thank you,
Это,
one, to Anatoly, because I couldn't have understood some stuff without Anatoly's work. And I have to say thank you to Ed Lewis, particularly for helping Matsumoto on his journey to understand that this was ball lightning. It was very important, and he recognized that you were a significant part of his journey.
Okay,
Yeah,
thank you.
Thank you. Значит, друзья, появился Эдвард Льюис. Эд,
Yeah.
we understood that you lost electricity on your computer.
Right. I
It's
forgot to
very
put in
strange. You should prepare carefully to your presentation, but no preparation. You worked on mobile. I see mobile mode without connection to the to the external electrical circuit, as I understand. Unfortunately, a lot of strange situation existing in your presentation, in your webinar, in your conference presentation, and now also. Now we start a study of discussion. Discussion will be in Russian, not in English, in Russian, and we don't need in your comment immediately now, but you will send me your comments when you will see the video record, and you will switch on mode of translation of video record, and after that you may send me back your response of this
Bob, is there a way, I mean, is there any way right now to put in a translation into English?
If you could, it was, but discussion will be in Russian. Друзья, начинаем дискуссию на русском языке, вот потому что мы сегодня услышали. Я попытался объяснить Бобу, что он может там потом как-то посмотреть и перевести, не Бобу, а Эду. И первый, давайте, вот Андрей Чистолинов хочет что-то сказать. Андрей, пожалуйста.
Да, добрый день всем. Но я с короткой репликой такой. Очень было приятно услышать, как двое американцев встретились и нашли друг друга на российском семинаре по шаровой молнии и холодному синтезу.
Второй не американец, Андрей.
Ну,
Второй
неважно, англичанин, да?
И не англичанин.
Не англичанин, а
австралиец. Только native English speaking.
Окей. Но надо сказать, что Эдвард, он как раз пришел... слышно меня?
Да, хорошо слышно, Андрей. И было видно, куда-то ты пропал. А Эд, куда-то ты пропал. Так, ну у нас
в институте сегодня связь плохая, интернет. Я вынужден был перейти с места на место.
Да, куда-то пропал, значит, вот исчез просто. Андрей,
Ну,
поэтому,
да,
Евгений,
вот
пожалуйста, твое выступление.
Да, сейчас слышно?
У меня не выступление.
Секундочку, вот Чистолинов возник.
Да.
Евгений,
дайте я договорю.
Ага,
Евгений, давайте договорю, поскольку я здесь.
Тебя никто не прерывал, ты просто исчез куда-то.
Да, я понял. У меня связь, видимо, тут
Давай, продолжай, пожалуйста.
Да, но я хотел сказать то, что Эдвард, конечно, по адресу попал к нам на семинар, потому что в нашем сообществе, по-моему, абсолютно большинство уверено, что существует какая-то связь между шаровой молнией и странным излучением, холодным синтезом, соответственно. Вот, но, и, кстати, очень мило было то, что Эдвард сделал слайды на русском. Просто тоже огромное спасибо ему за это. Но я должен сказать, что, вот как мне показалось, Эдвард, он в основном так, пытается образно-интуитивно вот что-то нащупывать. И, видимо, как нам кажется, во всяком случае, он правильно это нащупывает, но как бы дальше-то что? Вот мы тоже согласны с ним, что существует какая-то связь между странным излучением и шаровой молнией. Но следующий шаг какой? Вот этого шага я у Эдварда практически не увидел. То есть дальше должна, вообще говоря, следовать какая-то теория. И то, что предлагает Эдвард, это некоторые слова. Слова о том, что обычная материя, она вот может в какую-то непонятную форму перейти. Но дальше-то должна следовать стыковка, значит, должно следовать объяснение, как минимум, что это за материя, как она взаимодействует с обычным веществом и так далее, как она вот в это состояние переходит. Насколько я понимаю, у Эдварда ничего этого нет. А это ключевой момент на самом деле. И самое главное, как это все с современной физикой стыкуется. Ну вот такая реплика. А в принципе, ну да, вот мы думаем в том же направлении. Возможно, что Эдвард тут, можно сказать, у каждого второго из нас есть своя теория на этот счет. Вот, если Эдварду интересно, он может как бы со всеми нашими теориями познакомиться. Все, спасибо. Спасибо, я все
Спасибо,
сказал.
спасибо,
Да.
спасибо Андрею. Кстати, спасибо Бобу Гринье, который включил свою презентацию, и мы видим сабтайтлы на английском языке того, что мы говорим по-русски, и увидим, соответственно, русские субтитры на английские субтитры. Когда будут говорить по-английски, увидим русские субтитры. Спасибо Бобу Гринье. Спасибо, значит, вот Андрею, спасибо. Толь, пожалуйста, твое выступление.
Ну, я хотел бы, значит, поблагодарить тоже вот Льюиса, значит, за то, что Эдварда, за то, что он подготовил, значит, такой обзорный доклад. И, ну, вот все шаровики, значит, знают наперечет тех, кто занимается, значит, вот, ну, по крайней мере, с разных сторон изучением физики шаровой молнии. Вот. И Льюис там один из немногих, кто находится, так сказать, ну, часто цитируется и публикуется в зарубежной печати. В этом плане, значит, ну, я тоже так же, как вот Чистолинов, ожидал, что все-таки значит, будет продвижение в сторону, ну, так сказать, по крайней мере, значит, вот из наблюдаемых. То, что он рассказал нам, это уровень ботаники, когда по полочкам складывается материал, и это важный момент, с этого начинается наука. Дальше вот, значит, то, что предлагает Андрей, это вот, значит, все-таки зоология, так сказать. Вот, ну, давайте какие-то гипотезы строить. Значит, ну, мы не услышали ни одной гипотезы, к сожалению, вот у Эдварда, а очень жаль. Значит, здесь я согласен с Андреем, но, значит, все-таки гипотезы – это еще не есть теория. Теория – это всегда проверяется экспериментом, и, в общем, теоретическая модель уже предусматривает пролонгацию в плане планирования экспериментов с целью подтвердить те или иные качества вот этих неопознанных объектов, которые, ну вот, понравилось человеку назвать плазмоидами. Значит, вот на самом деле плазмоид сейчас уже в научной литературе вкладывается вполне определенный смысл, в котором, значит, вот все-таки магнитные силы, вот, или силы, связывающие, значит, вот воедино, значит, вот объект, то есть силы, значит, физические, но это могут быть не только силы Лоренца, но и могут быть, так сказать, там, химические силы, ну, допустим, поверхностное натяжение. Одна из моделей шаровой молнии была там с привлечением сил поверхностного натяжения. Вот, значит, но вот такой объект, он, значит, вот такие модели рассматривались вот в физике шаровой, значит, молнии. Вот. Ну и сейчас уже, по крайней мере, вот жаль, что Никитин вышел, я сошлюсь на него, по крайней мере, вот мы пытаемся проложить мостик между тем, что может делать, вот, ну, назвали плазмоид. Ну, ладно, вот эти вот, по сути дела, некие образования компактные, имеющие структуры. Это не плазма, это, безусловно, так сказать, не плазма, надо вводить новые определения. Может быть, не пятое состояние вещества, вот, может быть, это плазма, так сказать. Там же у плазмы много градаций. Выраженная, невыраженная, идеальная, неидеальная, структурированная, неструктурированная. Значит, много плазм бывает. Вот. Ну уж если совсем не подходит ничего, ну тогда да, давайте что-нибудь придумаем типа плазмоид, так сказать. Вот. Во всяком случае, шаровую молнию уже 100 лет пытается получить, и никто по-настоящему не получил ее. Вот. Но вот уже многие мосточки, вот и Юрий Николаевич Бажутов пытался сделать, просматривается связь между вот новыми высокоэнергетичными реакциями, ну, которые сейчас условно, опять условно, это как плазмоид, значит, называется Леннером. Никакого отношения, так сказать, возможно, к ядерным реакциям они не имеют. Но важно одно, что вот, так сказать, энергозапас шаровых молний, а такие калориметрические измерения природа делала, и не один. В общем, вот в ботанике, о которой говорил Эдвард, таких экспериментов по калориметрии много. Значит, и вот Никитин делал анализ, статистику этих вот, значит, Анатолий Никитин, этих наблюдений. Оказывается, что вот приблизительно шаровая молния имеет запас, верхний запас по энергетике где-то, значит, 10 девятый, ну, то бишь гигаджоуль, 10 девятых джоулей. Ну, если ты разделишь, вот, так сказать, на условную массу шаровой молнии, значит, вот размер известен, левитирует, ну, считается, что она по плотности, ну, почти как воздух, так сказать, вот, значит, ну, не такое, как Бычков говорит, ядро там пушечное, значит, но это не тонны. Вот. Получается, что, значит, энергосодержание в такой молнии приблизительно кевы на частицу. Приблизительно такие же кевы мы наблюдаем и вот в физике Леннер, так сказать. Никто вот больше, так сказать, ну, за исключением там немногих, так сказать. Во всяком случае, вот самые лучшие измерения удельной мощности в Ленре, это составляет, ну, десятки, ну, где-то приближается до сотни кев на атом водорода или атом металла. Вот это действительно очень напоминает, что по энергетике два объекта, значит, ну, очень похожи друг на друга. Когда гаснут шаровые молнии, ну, я как-то наберусь смелости, все-таки то, что мне известно по шаровой молнии, тоже расскажу ботанику. Значит, зачастую наблюдается, да, вот, так сказать, кучка, пирамидка, так сказать, значит, пепла, золы, которая почему-то ветром не раздувается, они держатся все вместе. Ну и вот такие анализы Воронежским университетом, Санкт-Петербургским университетом и вот, Томским университетом были сделаны. Значит, вот оказывается, что вот элементный состав очень похож на то, что мы имеем в трансмутации элементов при вот таких в реакторах, когда люди изучают Леннер. Вы обратите внимание, вот Леннер, если вы посмотрите эксперименты, сейчас уже начали, практически у всех групп начинают совпадать эти вот список этих элементов. Все ключевые элементы, они практически одни и те же. Ну, конечно, зависит от электродов, зависит от жидкости, от газа, есть специфика. Но, как правило, там рождаются однотипные элементы, которые у всех присутствуют вот, значит, в этом списке. Ну, достаточно сказать, что натрий есть всегда, калий есть всегда, этот, углерода да полно его, так сказать, вот, и так далее, и так далее. Вот. В этом плане и химический состав, вот то, что остается зола после шаровых молний, тоже напоминает, так сказать, Леннер. Поэтому вот эту цепочку аналогий можно рассматривать дальше. И вот Юрий Николаевич Бажутов, вот, и я долго спорили на эту тему, так сказать, стоит включать шаровую молнию, так сказать, в нашу конференцию, в наш семинар, вот, или все-таки это параллельные направления, пускай они пока идут, потом где-то, может быть, сомкнутся. Вот это единственное, наверное, наше сообщество, комьюнити, где мы все-таки пока не выкинули вот за борт, ну, значит, физику шаровой молнии. Ну и будем, так же, как Ленар, все-таки я согласен с вот Эдвардом, оставим пока, так сказать, плазмоидную теорию шаровой молнии как таковую, хотя она ничего нам не раскрывает с точки зрения физической модели. Это вот мой краткий комментарий его доклада. Спасибо большое.
Спасибо, Анатолий Иванович. Значит, ну, краткий комментарий, тем не менее, занял минут 10 примерно. Спасибо, тем не менее, все было очень по существу. Спасибо. Значит, Евгений Иванович, пожалуйста, Егоров.
Спасибо. Вот я не могу согласиться с Анатолием Ивановичем о том, что мы не умеем, так сказать, генерировать плазмоиды долгоживущие. Все-таки вот Вачаев и Иванов, у них рекорд.
Что-то не слышно тебя.
Евгений, у тебя там,
Постоянно
как там?
выпадает.
Ну, ты давай
Что?
повтори последние слова свои еще раз.
Вачаев,
Да у меня почему-то рука падает, и, в общем-то, неустойчивое соединение постоянно. так сказать.
Без ля-ля, давай, последние несколько предложений повтори.
Не согласен с Анатолием Ивановичем, что мы не умеем генерировать долгоживущие плазмоиды, то бишь долгоживущие шаровые молнии. Опыт Вачаева и Иванова тому пример. У них 2 с лишним суток плазмоид работал. Вот. Как его поддерживать, ну, для меня понятно. Ну и вот подход с использованием векторного потенциала магнитного электрического поля и первичного, нелинейного, подчеркиваю, нелинейного взаимодействия дает, на мой взгляд, очень плодотворные возможности к экспериментальному, широкомасштабному, так сказать, воспроизведению вот этих вот экспериментов. Спасибо. И
Евгений,
хочу еще, секундочку, вот все-таки, так сказать, не совсем понятно, слышал ли докладчик, то есть Эдвард Льюис,
Твой вопрос он
Вачаева
слышал.
Иванова.
Твой
Знает он
вопрос,
про эти работы?
Евгений, твой вопрос он слышал, но он на него не смог ничего ответить. Так, спасибо Евгению Ивановичу. Алексей Черепанов, пожалуйста, ваше выступление.
Оно у меня будет коротким. Спасибо Андрею Чистолинову, который снял у меня с языка все, что я хотел сказать. Ну, а Анатолий Иванович как бы дополнил все, что говорил Андрей. Я единственное, наверное, свою капельку такую маленькую капну, что вот природа шаровой молнии, плазмоидов и вообще все, что касается разрядов и так далее, с моей точки зрения, она лежит ну, в той идее, которую я продвигаю. Это речь о фотонной волне, о фотонной массе. Ну и отдельно, коротко сейчас хочу сказать для Эдварда, по-английски.
А у него перевод, это самое, Алексей,
wanted,
у него
to...
перевод снизу идет, по-русски говори.
Ну тогда так. Все, что я хотел сказать Эдварду, я разместил в тех комментариях в чате, которые он сможет по ссылкам скачать и узнать мое мнение. Вот и все.
Да,
я
чат разошлю. Алексей, спасибо за выступление. Так? Спасибо. Друзья, есть еще кто-то? Я больше рук не вижу. Тогда давайте я тоже несколько слов скажу. Значит, ну, во-первых, действительно, огромное спасибо Эдварду Льюису за то, что он попытался облегчить наше восприятие его выступления. Он очень старался, поэтому давайте мы его поблагодарим за это все. Ну, уже несколько человек об этом сегодня говорили. Ну и в целом спасибо ему за доклад, потому что я лично услышал несколько новых для себя вещей. Во-первых, ну вот я так вспоминаю, что о хвостах вот этих шаровых молний. Я вспоминаю, что наши основные вот докладчики по шаровым молниям, значит, вот они упоминают, основные, тут у нас несколько человек, пожалуй, 3, наверное, человека, упоминали что-то об этом, но как-то не очень активно. А вот Эдвард очень активно значит, об этом говорил, о хвостах. И вот это довольно новое для меня, что это очень, по сути дела, получается, что это ну, некая такая постоянная составляющая шаровой молнии. Вот я помню, Чистолинов там приводил длинный список свойств шаровой молнии, и что-то я там хвостов не припоминаю. Может быть, я не очень внимательно это все в свое время слушал. Поэтому вот это для меня новое. Но вот его идея о том, что шаровая молния – это она, и линейная молния – это одно и то же, просто это мы видим хвост шаровой молнии, вот это, по-видимому, может быть, ничем не доказанное предположение Эдварда Льюиса, но, как мне кажется, оно несколько преждевременно. Возможно, там более, ну, стандартное объяснение, мне кажется, более правдоподобное. И шаровая молния является уже следствием линейной молнии, что сейчас признается в основном шаровиками. Ну, вот это, мне кажется, более такая правдоподобная версия. Хотя физика разные обстоятельства допускает. Может быть, когда-то имеет место и то, о чем говорит Эдвард. Именно линейная молния является иногда или является проявлением быстрого, очень быстрого движения шаровой молнии. Возможно, это тоже имеет место. Теперь вот о плазмоидах. Смотрите, о термине, во-первых. Я хочу напомнить, что термин плазмоиды, он же ведь из астрофизики пришел на самом деле. Ведь плазмоидом там они называют такую вот область плазмы вот вокруг Земли, которая окружена замкнутым магнитным полем. И вот такой, знаете, магнитный мешок, если угодно. Вот. Ведь частицы по таким вот стандартным рассуждениям магнитогидродинамическим не очень охотно пересекают магнитные линии, им гораздо силовые линии, им гораздо удобнее двигаться вдоль силовых линий. Поэтому если магнитный мешок создать, то тогда там вот плазма, которая внутри будет, она там будет существовать, как бы не разлетаясь. Вот отсюда идея вот этих плазмоидов. Эта идея, она восходит еще к идеям термоядерной реакции сахара, вот этой бутылки, значит, вот магнитной. И потом вот эта идея, она правильно тут вот упоминал Климов о том, что она с помощью, по-видимому, капицы как-то перекочевала вот в лабораторные условия из космоса и, ну, и в другие более мелкие приложения. Ну, вот я хочу напомнить, что, во-первых, тут сегодня вот говорилось об определении плазмы. Я об этом несколько раз говорил и ссылался на Рухадзе, который в свое время очень четко и ясно сказал, что плазма, вот у Райзера есть определение плазмы, вот о чем говорил Климов, о том, что плазма – это, значит, вот смесь электронов, ионов и неионизованных атомов. Вот это у Рухадзе, у Райзера в книжке по физике плазмы. А вот Рухадзе, он серьезную поправку к этому определению дал и сказал, что плазма – это четвертое состояние вещества, это смесь электронов, ионов, атомов, неионизованных атомов с нулевым суммарным зарядом и электромагнитного поля. То есть 4 составляющие у четвертого вещества, 4 составляющие. Электромагнитное поле. Вот плотность электромагнитного поля, вот электромагнитное поле является очень важной составляющей. И сегодня уже говорилось, и я очень эту идею поддерживаю, мне кажется, что шаровые молнии и наши процессы, которые мы изучаем, они в первую очередь отличаются плотностью электромагнитной энергии, которая ответственна за процесс, который вот мы называем там Ленером, который называют шаровой молнией, который называют неизвестным излучением, который вы все называете, в основном все называете странным излучением. Вот эта плотность энергии ответственна за этот процесс. Ну вот Климов назвал величину 1 килоэлектронвольт на частицу, а я бы ввел понятие энергии, ну можно ее и в килоэлектрон-вольтах, не на частицу, а на единицу объема, что более важно, мне кажется. И вот это, может быть, я как-нибудь что-нибудь на эту тему попишу отдельно, потому что вот это, мне кажется, очень важно, потому что там энергия может существовать, мне кажется, в результате и без такой стандартной известной частицы, такой как электрон или там протон, к чему мы привыкли. Вот это мое первое замечание, соображение. Ну, сегодня вот следующее соображение. Вот сегодня некоторые авторы говорили о том, что мы прослушали очень интересную лекцию, там подобран материал такой интересный, но все-таки это никаких теорий мы тут не увидели, не услышали. Я вот такой подход называю наблюдательная физика, observational physics. Это не физика формул и каких-то теорий, а это физика регистрации явлений. И вот, возможно, на этом этапе, на котором мы находимся, такой вот регистрация явлений, такая вот наблюдательная физика крайне важна. Она помогает понять, а чем же мы, собственно, занимаемся. Поэтому я бы не отвергал этот подход, он мне представляется не лишним. Теории тоже нужны, эксперименты тоже нужны, но и наблюдательная физика, не эксперименты, а именно наблюдательная физика, она тоже нужна. И я напоминаю, что вот люди, которые занимаются шаровыми молниями, они это давно сообразили. Вот стало ясно, что такие вот простецкие подходы к физике плазмы, которые там величайшие люди, там Кадамцев, там Смирнов, там прочие, самые лучшие наши, значит, вот плазменщики пытались что-то сделать, ничего не получалось. И стало ясно, что, возможно, наблюдательная физика и тоже важна, и она позволит как-то продвинуться. Для меня
Фарадей
было...
этим занимался.
Кто?
Я говорю, Фарадей занимался этим.
Ну и да, ну в частности, да, ну не было, как только нет теории, люди начинают с наблюдательной физики. Спасибо Черепанову за подсказку. Так вот, это не надо отвергать, мне кажется, это тоже очень важно. Поэтому спасибо Эдварду. Но у нас такие люди есть. Вот я напомню, что вся вообще, по сути дела, в основном шаровая вот тематика у нас, она, на мой взгляд, в первую очередь основывается на наблюдательной физике. А теории, которые они строят, они еще, на мой взгляд, просто очень сильно сыроваты. Вот. Ну и еще одну вещь, я закончил с этой частью, и еще одна вещь, мне кажется, очень важной, это вот о black черные, темные, значит, вот эти плазмоиды, о которых говорил сегодня Эдвард Льюис. Я, честно скажу, я первый раз про это услышал. Кстати, спасибо Эдварду, что он упомянул несколько российских, значит, вот исследователей, которые внесли вклад в регистрацию, он не всех упомянул, но некоторых, которые внесли вклад в регистрацию вот этих явлений, связанных со следами. И в частности он упомянул моего ближайшего коллегу Диму Баранова, который действительно очень интересные в свое время опубликовал фотографии, следы, которые он регистрировал, в частности, на, вот, значит, на детекторе альфа-частиц, которые были, это такой очень хорошо полированный кусок золота, покрытый золотом, и он весь был исчерчен разнообразными следами, и вот часть из них сегодня показывал Эдвард Льюис нам. Поэтому вот эти, да, вот это вот черные, вот эти черные плазмоиды, для меня это новое. Насколько я понял доклад, черные плазмоиды – это когда свет не проходит через какую-то часть пространства. Я вот обращаю внимание, что мы, вот многие, кстати, первыми, кто обнаружил, я думаю, что это наша лаборатория вот с Барановым, лаборатория ЛИС, мы обнаружили, что обычное рентгеновское излучение почему-то плохо проходит через пространство в лабораториях, в которых активно проводятся эксперименты. Потом это подтвердили многие люди, некоторые из них даже ссылаться забывают, а может быть даже не знают. Вот я напомню, что, вот, или вернее хочу сказать, что мне кажется, вот эти темные плазмоиды, черные, вернее, плазмоиды, black, вот это английское слово black, это именно черные плазмоиды, они поглощают, черное это то, что поглощает. Вот это хорошее слово для этих участков пространства, который поглощает не только свет, но я думаю, что если бы проводить измерения в рентгеновском спектре, там тоже были бы поглощения вот в этой области. Хочу напомнить, что вот в нашей лаборатории ЛИС, мы в свое время выдвинули идею Dark Hydrogen. Вот это не black, а dark. Это значит темный водород по-русски. Так вот, не черный, а темный. И не тяжелый, как некоторые говорят, а просто темный водород. Dark Hydrogen. Вот эта идея, она, вот мне кажется, многие, я просто сейчас не хочу в это уходить, но она многие явления, которые вот сегодня рассматривал, наблюдательные явления рассматривал Эдвард Льюис, она довольно просто, как мне кажется, объясняет. Друзья, еще раз хочу поблагодарить Эдварда Льюиса за подборку таких вот наблюдательных явлений, связанных с молнией. И отдельно хочу поблагодарить его за анализ, ну, можно так сказать, общественных, социальных проявлений, возможных общественно-социальных проявлений нашей активности в физике, что было в его первой части, его выступления. Друзья, я закончил. Эд, ты видел, вот слышал и, наверное, понимал, глядя на субтитры, о чем мы говорили, и тебе вот заключительное слово. Ed, you may have a floor to say some final words on this webinar.
Okay, спасибо. Thank you very much for this time, and I really actually enjoyed it. I think Bob put the translation here so I could read what you were saying. Actually, the translation is terrible, but I can understand about 80% of what you're saying. So thank you very much. This is a good time.
That's all what you would like to say?
Yeah, I mean, I hear your question and comments, but I think you said later I should try to write something and send it to you. Yeah, those are very, very good questions, and to answer those questions takes
Okay.
maybe 2 pages, 5 pages, I don't know.
Окей. Эд, наверное, потом, друзья, потом нам чего-то напишет, более подробно изучит то, о чем мы тут наговорили сегодня. И еще я вот эти его реакции разошлю. Друзья, у нас сохранилась, тем не менее, приличная аудитория. Спасибо тем, кто вот дожил до вот этого времени. И на вот этом довольно сложном в языковом плане вебинаре. Спасибо еще раз Эду. В следующий раз, друзья, мы увидимся 20 ноября этого года, 2024 года. Всем спасибо еще раз. До встречи 20 ноября.
До свидания.
Okay.